Welcome to Nuclear Chemistry Part 2. Here we'll take a closer look at the types of radioactive decay that were introduced in the first tutorial. Let's get started. Right? So we saw in the previous tutorial that a nuclear reaction creates a change in the composition of the nucleus of the atom. Right? So initially we talked about radioactive decay, where the unstable nucleus ejects some subatomic particles or high energy photons of light to become more stable. The other reactions that we'll look at in our last tutorial are fusion. This is what happens in stars and the sun, right? Nuclei combining into larger nuclei, or fission. And this is where we split the nuclei of atoms. And this is what we use for nuclear power plants and for bombs. All right, so here's a quick recap of what we learned about in the first tutorial, right? The different types of radiation and their symbols. And notice their symbols can be written to show how it impacts the nuclear structure. And there's the mass and the charge, all things to help keep in mind. And now here's some new information. The ability to penetrate. Notice that alphas have very low penetration. Betas and positrons simply differ by the charge, and so those also have relatively low penetration. And then the gamma rays and the neutrons have very high penetration. So quite logically then, the shielding required is going to be based on the penetrating ability. So something with very low penetration, like an alpha particle, our clothing will stop them. And even with the beta particles, just if we have heavy cloth or plastic, will stop the beta and positrons particles, and they will not be able to get into our body. However, gamma rays and neutrons, with their very high penetrating ability, we need lead, concrete, or water. And so quite logically then, that influences the biological hazard, right? So things with low penetration, as long as they stay outside us, they're not going to hurt us, like alphas. And notice for betas, it's pretty much would be the uncovered parts, right? The exposed parts of our body would have the greatest hazard. And then with the gammas and the neutrons, they're just going to completely penetrate through us. So some other interesting things to keep in mind, right, is that nuclear decay does not depend on the environment of the atom. There is nothing we can do to stop an unstable nucleus from decaying. There are time rates, and we'll talk about that in our half-life tutorial. So we can't put them in a special temperature, a pressure. There's no magic compound to stop radioactive decay of an unstable nucleus. But we can use this to our advantage. All nuclear reactions are exothermic, and they release huge amounts of energy, orders of magnitude higher and larger than what we see from a pure chemical reaction with chemical bonds. And in a future tutorial, we'll look at those values a little more closely as well. But for now, we'll focus on the radioactive decay. So we'll start with alpha decay. And the key is really in the balancing, right? So just remember conservation of mass. Right? So matter cannot be created nor destroyed. So if we look here, we see uranium-238 will decay into thorium-234, releasing an alpha particle and a gamma ray. Right? So when we see the alpha particle, remember to think about the helium nucleus. And so if we look here, right, I think I'll just wait to talk about a little bit more, right? So what type of radioactivity was released, right? The alpha particle and gamma ray. Okay, and so Why was the gamma ray released, right? Because this was excess energy. So the nucleus was stabilized by being converted into the nucleus of thorium-234 and a alpha particle, but there was still some leftover energy, right? So then that's also conservation of energy. So we can practice all of our balancing skills for reactions. All right, so how does the total number of protons in the reactant compare with the total number of protons in the products? So if we look here, we'll see, right, that we started with 92 protons on the reactant side, and then we have 90 plus 2. So we have 90 protons plus 2 protons. So we see, right, that it's the same. So we have the same number of protons. And now if we look at the mass number, right, 238, so the total number of protons and neutrons was 238, and now we have the 234 and the 4, which of course adds up to 238. So notice, right, the same value for A. Okay. And then last but not least, right, does the gamma ray affect the mass balance of the reaction? And if we look here, we would say no, right? We need the gamma ray, right? This is about the energy balance. Okay, oops, let me slide that up, right? So the gamma ray is about the energy balance, right? It's not about the mass balance. So, is the nuclear reaction above balanced? Yes. For both, right, if we look, right, the alpha particle helps us to address the issue of mass balance, and then in this case we have a gamma ray here, so that the energy, right, the energy here on the reactant side equals the energy on the product side. Okay, so now let's have you practice. So down at the bottom of the page, there is a reaction, right? So remember when we see the alpha particle to think about the helium nucleus, right? So we had 86 protons to start, 2 are lost, so we recognize that our daughter will have 84 protons. And then if we look at the 222, right, minus 4, so then that would be 218. So once we found the Z, the atomic number, and 218, the mass number, we can go to the periodic table. What element has 84 protons? Polonium. All right, so it's that simple to balance a nuclear reaction with the release of an alpha particle. Okay, now we'll look at beta decay and positron emission. So we'll start with beta decay, and this happens when we have neutron rich. And it's interesting, the beta particle, we could think of it as having a minus. It's typically not written, right? So we have a neutron, and it is going to convert into a proton. And if we think about the charges, right, neutrons are neutral, protons have a positive charge, right? So then there's our beta with the minus, right? So we can note the charge balance. Okay, and then the symbols down here will help us with doing our reactions, right? So beta particles are produced from an unstable nucleus when a neutron is transformed into a proton, releasing a high energy electron, also called a beta particle. Alrighty, so if we look here, right, so for me it helps to just go, oh, a neutron became a proton plus a beta. So if with this parent, I know that one of these neutrons becomes a proton, so I'm going to add, right? So this will become 55. Or if you want to think about it using the symbol here, right? 54 minus 1, which would be 54 plus 1, or 55. And notice that the overall number of protons and neutrons doesn't change. So the 133 stays the same. So we look at the periodic table and we see that cesium has an atomic number of 55. And then there's our beta. Okay. Now for positron decay, it's the reverse. Now we have a proton-rich isotope. And so one of the protons is going to convert to a neutron, right? So protons have positive, neutrons are neutral. Now we have our positron, right? So once again, note the charge balance. Mass is balanced as well, but that doesn't help me as much, so I don't emphasize it, right? So the positron is produced from an unstable nucleus when a proton is transformed into a neutron, releasing a high energy positron. Alrighty, so now we'll try one here, right? What was the parent that produced this daughter, right? So for me it helps to go, okay, the proton became a neutron plus a positron. So if I look here, this lost a proton. So this would be 37. Or we could simply say 36 plus 1 is 37. All right, so either way we think about it, whether we think about what's actually happening inside the nucleus or use the mathematics of the symbol, we get a 37. And we know that the total number of protons and neutrons stays the same. So our mass number remains 79, and our atomic number has increased to 37. And so this would be rubidium. Okay, so that's about as tricky as it gets. Now we'll look at gamma rays. We'll look at the electromagnetic radiation, or light, a little more closely to fill out our understanding there. All right, so X-rays and gamma radiation are high energy light. The energy of light is equal to h nu. So h is Planck's constant. We're not going to worry about that. The nu here, that is frequency. That's the Greek letter nu. And we can also write it as hc over lambda, right? So lambda is the wavelength. And of course, c is the speed of light. And so what we can see here, we talked about this on a previous tutorial, right? This is where we're high energy, all right? So if we're high energy, we have a short wavelength and we have a high frequency. And down here, when we're at low energy, we have a long wavelength and a low frequency, all right? And then I think it's also helpful to understand the relative energies of the different regions of the electromagnetic spectrum. And so a common example of a pure gamma emitter would be technetium-99m, a very commonly used radioisotope for nuclear medicine. So remember that the M part tells us that it's high energy. And so then what it does is it decays to technetium-99, and then it releases the gamma ray. So this is lower in energy, and then here is the energy difference, right, between 99m and 99. All right. Okay, so now let's put this all together. So here is a decay series for uranium-238. And notice that a lot of times when we have a decay series, so uranium-238 was unstable, but it has to decay all the way to lead-206 to actually become a stable nucleus. So let's look at this more closely. Right? So here's our mass number A along the y-axis. And then here is our atomic number Z along the x-axis. Right? So this is the number of protons. And this is the number of protons plus the number of neutrons. So now if we look here, right, we can do the math. We see that we start at uranium-238, and notice that we're going to have a loss of 4 mass units and 2 protons. So this is an example of alpha decay. And then we notice that the thorium-234, it decays to, I think that's protactinium, so there's a, and then back to another isotope, right? So that would be 234 of uranium. And then we get a series of alpha decays all the way down until we get to lead. And then we have a couple more beta decays. And then that leads us to another alpha. And then 2 more betas. And finally, we get to an alpha, and now we have our stable isotope. All right, so you want to be able to look at a chart similar to this and be able to distinguish between the alpha decay and the beta decay of a radioactive isotope. And then the other way that I can ask you questions is to look at reactions similar to what we did in the previous pages. So this would be a good time to pause the video and do your best to answer these. Of course, now they're out of context, so we have to be able to discern which process is occurring. Alrighty, so here we have xenon-118, and we notice that it releases a positron, right? A beta plus. So this piece here is telling us we started with a proton and it went to a neutron plus a beta particle. So we get all of that from knowing that it's positron emission. All right, so that means one of the protons in our parent was converted to a neutron. The other way to think about this, right, so this would be, this is the +1, 0, right? So 54 minus 1, so that would be 53, and the mass number doesn't change, and so we have produced the isotope iodine-118. Now for this next example, let's look here. We have an alpha particle, so that's our helium nucleus, right? And then we have our gamma ray, the bent off extra energy. So based off of mass balance, we started with a parent of 84 and we've lost 2. So that would mean that our daughter has only 82 protons and 206 for the mass number, right? And so now we look on the periodic table and we see that this is lead. Okay, and the last one here, let's see, we have potassium-40 decaying to calcium-40. So notice what happens here. Notice that we have a neutron becoming a proton, which would mean we would have to release a beta particle. And, or if you'd like, if you're more comfortable, we can use the -1, right? And so then we know that 19 minus -1 would be 20, whoops, which gave us the calcium. So we can identify either the products, the daughters, or the radioactive particle emitted. So now would be a great time to work through some extra homework problems to reinforce your understanding of nuclear decay reactions. You want to be able to look at a graph or a reaction and either predict the parent, the daughter, or the subatomic particles released.